Throughout this course, we'll often be inspired and uplifted by great infrastructure systems, like the Catskill Aqueduct, the electric power grid, the interstate highway system, and the global positioning system, all of which represent triumphs of human spirit and ingenuity. But today, we'll be talking about sewage. While it's hard to find anything inspirational or uplifting about your local sewage treatment plant, there is something quite extraordinary about what this facility actually accomplishes. It takes sewage, or more properly, wastewater, a foul, unhealthy byproduct of human existence, and it restores it to crystal clarity, and then returns it to nature without harming the environment. In that sense, wastewater treatment is as much a triumph of human ingenuity as is the Hoover Dam. Having said that, if you've just eaten a meal, you might still want to skip ahead and return to this lecture later because we will be talking about sewage. Our pungent exploration of wastewater disposal and treatment begins precisely where our exploration of water distribution left off, at a plumbing fixture in your home. Now, in general terms, a fixture is a device that draws clean water from the distribution system and discharges wastewater into the sewage system, without allowing any flow in the opposite direction. The most common residential plumbing fixtures, toilets, showers, bathtubs, sinks, and washing machines, all share this fundamental characteristic, a distinct break between clean water flowing in and dirty water flowing out, with no opportunity for the bad to contaminate the good. The purpose of your household plumbing system is to capture the wastewater discharge from all these fixtures and combine it into a single stream for disposal. This stream is composed of over 99.9% water, a number that seems quite surprising until we recognize that the combined effluent from your sinks, showers, tubs, and washing machine far exceeds that of your toilets. The remaining 0.1%, somewhat euphemistically called suspended and dissolved solids, is a complex and potentially unhealthy mixture that includes dissolved organic material, which originates from both human waste and food, suspended inorganic particles, or grit, rags, paper, plastic, and similar materials that somehow get flushed down toilets, and a high concentration of enteric microorganisms, bacteria that originate in our intestines and may include some pathogenic or disease-causing forms. This is the stuff that all wastewater treatment systems are designed to remove. So let's look at some general characteristics of these systems. In the US, about 75% of residences send their wastewater through a sanitary sewer network to a centralized sewage treatment facility, which cleans the water and discharges it into a natural watercourse. The remaining 25% of residences, primarily in rural and suburban areas, use on-site septic systems. During this lecture, we'll focus primarily on the centralized treatment facility, but I'll conclude with a quick overview of on-site septic systems as well. Regardless of configuration, wastewater systems operate primarily by gravity-driven flow. Thus, with only a few exceptions, every conduit in the system, from that 1-inch pipe that drains your bathroom sink to the 4-foot diameter sewer main carrying an entire city's effluent to the treatment plant, must be placed at a carefully controlled downhill slope or gradient to ensure the steady movement of the wastewater through the system. Yes, as the old saying goes, the stuff really does flow downhill. And that's why you're quite likely to find your wastewater treatment plant at the lowest point in town. Now, let's return to the portion of the wastewater system that's closest to home, your plumbing. We've already seen half of your plumbing system, the final segment of the water distribution network that delivers purified water under pressure to your fixtures. Now we'll see what happens when this same water goes down the drain. The central spine of your residential wastewater system is a large diameter vertical pipe called the soil stack, extending from above your roof, where it serves as a vent, straight down to your basement floor or ground level slab, where it connects to a gently sloped underground pipe called a lateral that feeds into the municipal sewage system or your on-site septic tank. In residential plumbing, most wastewater pipes originate at fixtures and they end at the soil stack. Building codes also allow fixtures other than toilets to empty into a smaller vertical drain pipe called a secondary stack, as you can see here. In either configuration, every pipe running from a fixture to a stack must be mounted on a gradual downhill gradient along its entire length, with one important exception: this U-shaped bend located directly beneath each drain. It's called a trap, and it's one of the most important features of your plumbing system. Let's see how it works. Though configurations vary, there's a trap directly beneath every drain in your home. And because of its shape, the trap is always filled with water, as you can see here. This water forms a plug that prevents noxious gases from re-entering your home from the sanitary sewer, which is located down here. So note that as I pour wastewater down the drain, some quantity of water will overflow from the opposite side of the trap, but the amount of water in the trap will remain unchanged. And that amount of water in the trap provides an airtight seal and continues to provide an airtight seal no matter how much water is passed through the system. Now, this vertical pipe up here is called a vent. Every wastewater line in your plumbing system has one. And as you can see in my model, each vent either runs up through the roof or alternatively, it might connect to the upper end of the soil stack, which also extends up through the roof and is open to the air. The purpose of the vent is to ensure that atmospheric pressure is maintained on either side of the trap. Without it, wastewater rushing down the drain pipe can create a partial vacuum. This vacuum can actually suck the water right out of the trap, breaking its airtight seal. Now, to demonstrate how the vent works, I'm going to plug it up using this cork, which effectively removes the vent from the system. And then I'll dump a large quantity of water down the drain. Watch what happens. Wow, there it is. Because the vent was closed off, most of the water was sucked out of the trap. And if you have any doubt that there's a partial vacuum in this system, you only need to look at the water that's remaining in the trap. Notice that the water level on the left side is significantly higher than the water level on the right. And to demonstrate that this is a result of the pressure imbalance, all I need to do is remove the cork, and you'll see the two water levels equalize themselves as soon as atmospheric pressure is restored to both sides of the trap. Now, before we leave the subject of plumbing fixtures, let's spend a few minutes examining one of the world's most unappreciated technological marvels, the flush toilet. Most people use this device many times a day, yet have only the vaguest notion of how it actually works. Let's uncover the mystery. Here's a typical US-style toilet, composed of a bowl and a tank, both currently filled with water. The water in the bowl is controlled by this built-in S-pipe, which at various times serves as a drain, a trap, and a siphon. At the moment, it's working as a trap. Pour some additional water into the bowl, and the same amount will overflow this bend in the S-pipe. And like the U-shaped trap we just examined, this plug of water keeps foul-smelling gases from entering your home from the sewer system. Water is retained in the tank by this hinged rubber plug called a flapper flush valve, which closes off the flush tube that connects the tank to the bowl. Now, press the flush handle and the fun begins. As the handle rotates, this lift arm pulls a chain. that lifts the flapper flush valve off of the flush tube. When the valve is closed, it's held in place by the weight of the water above it. But as soon as that seal is broken, the buoyant valve floats upward, allowing the water in the tank to flow rapidly down the flush tube into the bowl. This sudden rush of water fills the bowl faster than the S-pipe can drain it. And when the water level in the bowl exceeds this uppermost bend, it completely fills the S-pipe and creates a siphon. As the water pours down the vertical drain pipe, the siphon creates a strong suction that quickly and powerfully pulls the bowl's contents along with it. Only when the water level falls below this lower bend can air re-enter the S-pipe. At this point, you'll hear a distinct gurgling sound as the inrushing air breaks the siphon, and the flow of water from the bowl abruptly stops. Meanwhile, back in the tank, as the water level drops, the floating flapper flush valve settles back onto the flush tube and stops the outflow. Simultaneously, this float on the end of the lift arm also falls with the water level, opening a fill valve here that directs a stream of fresh water into the tank through this fill tube and into the bowl through this one. The bowl refills to its previous level, controlled by the curve of the S-pipe as before. When the water in the tank reaches its original level, the float on the end of the lift arm provides the force necessary to shut off the fill valve, and the system is ready for another flush cycle. And if anything goes wrong with a shutoff, this overflow tube prevents the water from overflowing the tank. Wow, what a wonderful apparatus. Yes, I know, it's only a toilet, but think about the interconnected series of mechanical and hydraulic events that are initiated by the simple push on a handle that proceed with no external power source apart from the pressure in your water supply system, and that incorporate ingenious mechanisms for self-regulation and shutoff. Furthermore, think about the array of scientific principles at work here. The principle of the lever, conversion of potential to kinetic energy, buoyancy, open channel flow, pipe flow, siphon flow, and many more. When this lecture is over, you're probably going to need a trip to the bathroom anyway. While you're there, take the lid off the tank, hit the lever, and just watch as this marvel of everyday engineering does its job. Okay, now let's return to the big picture. As wastewater flows from the soil stack, it enters either a municipal sanitary sewer system or an on-site septic system. The sanitary sewer begins with a lateral. That's the underground pipe that runs from your soil stack to the street, where it connects to a larger pipe called a branch. Branches feed into progressively larger pipes, typically called trunks and interceptors, in a tree-like topology very similar to the one we saw in storm drainage systems. Sewer pipes can be made of concrete, iron, vitrified clay, or PVC plastic. In large municipal wastewater systems, the interceptors can be huge. A 48-inch diameter concrete pipe is fairly typical. Now, sanitary sewer lines usually follow public streets, and they always follow a steady downhill gradient unless the topography prevents it. The slope of a sewer pipe is designed such that the flow is fast enough to keep those nasty suspended solids moving, but not so fast that this gritty liquid erodes the insides of the pipe. In cases where topography prevents a continuous downhill gradient, a sewage lift station is installed to pump the wastewater stream to a higher elevation, at which point it resumes its gravity-driven downhill flow. In times past, sewage lift stations were sometimes housed in architecturally elaborate structures, like this one in London, perhaps to distract us from thinking about what's actually happening inside. But today, lift stations are far more utilitarian. Sewer pipes are often the deepest buried of all utilities. Yet right here in the middle of your street is a telltale sign of their existence, a chain of manhole covers, which provide access to the sewer line for maintenance and repair. The manhole itself is really just a vertically oriented concrete cylinder, typically located where the underlying pipe intersects with another sewer line or changes direction or slope. Which brings us to one of the great philosophical questions of our time. Why are manhole covers round? Well, you've probably heard the standard answer to that question is that a circular cover can't accidentally fall through the manhole. And this is certainly true. Assuming that there's a narrow supporting lip around the inside of the hole, the circular cover, turned edgewise, can't possibly fit through the hole. While a square manhole cover can fit through the hole quite easily, as can a triangular cover. But in this respect, other shapes, like this rouleau triangle, will actually work just as well as a circle. Because of the unique rounded shape of this triangle, it too can't fit through the hole in any orientation. If we make the supporting lip wide enough, it's also possible to have an 8 or 10-sided polygon like this one work just as well, in that it too is unable to fit through the hole. Polygonal shapes do have a disadvantage though, because they can fit into the hole in just one orientation, whereas the circular manhole cover can fit in any orientation. And of course, a circular cover can be moved around quite easily simply by rolling on its edge, while the other shapes can't. And that brings us to the city of Nashua, New Hampshire, reputed to be the only municipality in the United States with triangular manhole covers. We've already seen that a triangular cover can easily fall through its manhole. So what advantage could there possibly be in using a triangular cover? Well, they are distinctive. And in my view, creating visually interesting infrastructure is a worthy thing to do in and of itself. The manufacturer of Nashua's manhole covers also claims that they rattle less than a circular cover when a car drives over them. And this has a ring of truth, because as you learned in your high school geometry class, a plane is uniquely defined by 3 points. That's why a 3-legged stool only needs 3 legs and never wobbles. But the most practical reason that a triangular cover works is that it can point in the direction of sewage flow. And I know this is an important thing to know because every time I walk through my neighborhood, I notice that the city sanitation workers have painted these green arrows at each manhole to indicate the direction of flow. The triangular manhole cover accomplishes this purpose permanently without any of this unsightly graffiti. By the way, outside of Nashua, most manhole covers aren't terribly interesting, but there are some wonderful exceptions in places like Galveston, Louisville, and many cities in Europe where the lowly manhole cover has become a symbol of civic pride, perhaps even comparable to a water tower. And to these cities, I can only say, bravo. Well, like wastewater flowing through a sanitary sewer, we've now reached our principal destination for this lecture, the wastewater treatment plant. A wastewater plant has essentially the same purpose as a water treatment facility, and it actually uses many of the same types of equipment. But where water purification relies primarily on mechanical and chemical processes, wastewater treatment also heavily depends on biological processes. Let's see how a typical wastewater treatment plant works. Treatment begins as the wastewater stream enters through a series of trash racks, metal grills, that filter out large pieces of debris and foreign objects. From here, the flow enters a grit chamber, which is designed to settle out the larger suspended particles like sand, coffee grounds, and watermelon seeds, to keep them from damaging pumps and other equipment at later stages of treatment. Next, the wastewater enters a sedimentation tank, also called a primary clarifier, like this one. The stream is pumped in from the center, and then it flows very slowly toward the outer perimeter. Along the way, floatable contaminants rise to the surface and form a greasy scum that's removed by a skimmer mounted on this rotating platform. Simultaneously, heavier material settles to the bottom as sludge and is raked into a sump at the center of the tank and then pumped out. Here are the rake and sump visible in an empty tank. Now, after about 2 hours at the clarifier, the wastewater has shed most of its floatable scum and suspended solids. It's now decanted over the rim of the tank like this and collected in a trough below. At this point, the water is said to have undergone primary treatment. Now, in years past, primary treatment, a purely physical process, was often the only purification that wastewater received before being returned to a river or stream. But today, secondary treatment using biological processes is required by federal law to meet modern water quality standards. The fundamental challenge in secondary treatment is a phenomenon called biochemical oxygen demand, abbreviated BOD. Water naturally contains dissolved oxygen, which it acquires through contact with the air and from the photosynthesis of algae and aquatic plants. Dissolved oxygen is critical for the health of an aquatic ecosystem because fish and other aquatic animals need it to breathe. Most water also contains some organic compounds, like those dead algae we encountered in our lecture on water purification. Aquatic bacteria and other microorganisms consume these organic compounds as food. This decomposition of organic compounds involves oxidation, a chemical process that consumes dissolved oxygen in the water. And within a body of water, the population of these microorganisms tends to increase in proportion to the availability of food. Well, as we've seen, wastewater is loaded with organic material, primarily from human waste, even after primary treatment. Thus, we say that the wastewater has a very high BOD, biochemical oxygen demand, because those tasty organic compounds are present in abnormally high concentrations, and the resulting large population of hungry microorganisms severely depletes the quantity of dissolved oxygen in the water. A BOD is typically expressed in milligrams of oxygen consumed per liter of water. It's determined by taking a sample, measuring its concentration of dissolved oxygen, then incubating the sample for 5 days at a constant temperature of 20 degrees centigrade in the dark so that no additional oxygen can be produced by photosynthesis, and then measuring the dissolved oxygen again. The biochemical oxygen demand is the difference between the concentrations of dissolved oxygen before and after incubation. Well, high BOD is a big problem. But in one sense, it's also a self-correcting problem. If wastewater with high BOD is discharged into a stream, the high concentration of microorganisms will consume most or all of the dissolved oxygen downstream of the discharge point. Then the microorganisms will die off for lack of food, and then the stream will eventually be able to replenish its dissolved oxygen through contact with the air. The problem, of course, is that along the entire water course where this natural biological process is occurring, the fish will suffocate for lack of oxygen. The primary purpose of secondary treatment, then, is to take advantage of this natural biological process, but to move it inside the treatment facility where it will do no environmental harm. The most common technology for reducing BOD to safe environmental levels is the rather colorfully named activated sludge process. In this process, the wastewater stream is directed into a series of deep vats called bioreactors, where it's combined with carefully managed populations of bacteria, protozoa, worms, and microscopic animals called rotifers. These microorganisms rapidly consume the organic compounds in the water and thus reduce its BOD under controlled conditions. Now, this process requires lots of oxygen, and so activated sludge reactors are always vigorously aerated, either by mechanical agitators, as you see here, or by streams of air pumped up from the bottom of each reactor. In either case, it's always easy to spot the activated sludge reactors at a treatment plant. They're the ones filled with bubbling, roiling, frothing brown liquid. Environmental engineers call this foul stuff mixed liquor, but an enticing name doesn't make it any more appealing to me. Its appearance notwithstanding, mixed liquor is actually being purified by an army of bacteria and bugs conscripted especially for this purpose. Now, having introduced all these critters into the effluent stream, we need to get them back out. And we need to do it gently because they're still hungry and they're quite willing to continue consuming these troublesome organics in the next batch of wastewater. Thus, the stream is now transmitted into a secondary clarifier tank where the mixed liquor is stilled, the microorganisms settle to the bottom, and a portion of this activated sludge is returned to the reactor to reseed the biological treatment process. The clarified water is drawn off. It's sometimes passed through a filter to remove any particulate matter that didn't settle out in the clarifier, and then it's disinfected with a final dose of chlorine to kill any remaining bacteria. The water is now clean and quite safe for discharge into the local stream through a conduit called the outfall sewer. However, all of that sludge collected from the clarifiers and filters still needs to be treated. This is accomplished through another biological process called anaerobic digestion, bacterial decomposition in the absence of oxygen, which takes place in these sealed, heated tanks. The products of anaerobic digestion are methane gas, which can be collected and burned as fuel, and this solid residue, which after dewatering can be used as fertilizer. The typical wastewater treatment plant is a major industrial facility that uses complex physical, chemical, and biological processes to treat millions of gallons of sewage per day. At the opposite end of the technological spectrum is the on-site septic system, used by a quarter of all residences in the US. An on-site system consists of two major components, a septic tank and a drain field. The typical septic tank is a large, closed, watertight concrete container with a capacity of 1,000 to 2,000 gallons. Installed with its top just below ground level, with an inlet from your sewage lateral at one end and an outlet to the drain field at the other. Now, when wastewater enters the tank, the floatable contaminants rise to the top and they form a thick layer of scum. The heavy suspended solids sink to the bottom, where they decompose anaerobically. Note the T-shaped inlet and outlet pipes, which are specially configured to prevent the inflow and outflow from intermingling with the already segregated contaminants in the scum above and the sludge below. Wastewater flowing out of the septic tank has lost much of its suspended solid material, but is still loaded with those organic compounds, which must be removed by the drain field, a series of perforated plastic pipes up to 100 feet long, placed inside a gently sloping trench surrounded by a bed of crushed stone and covered over with soil. Wastewater flows through these perforated pipes, and then it seeps out through the bed of stone and into the soil below. The stone accumulates a thin layer of those same helpful microorganisms that feed on organic material, and the combined action of these organisms and filtration provided by both the stone and soil cleans the effluent effectively enough to prevent environmental damage. The most impressive characteristic of this system is that it actually replicates all of the major processes in a wastewater treatment facility: sedimentation, flotation, anaerobic digestion of solids, filtration, and activated sludge treatment with no moving parts whatsoever, and with human intervention required only to pump the sludge out of the septic tank every few years. The downside is that an on-site septic system requires a fairly large piece of land, and it only works well in soils with just the right degree of permeability, high enough for the wastewater to percolate out of the drain field, but not so high that the wastewater moves through the underlying soil too quickly to be fully treated before reaching the water table below. However, in cases where the natural soil properties are inadequate, it is possible to construct the drain field above ground, embedded within a mound of imported soil with the right permeability characteristics. This mound doesn't do much for the aesthetics of your yard, but it does work. Because a failed septic system can do significant damage to the local ecosystem and water supply, these systems are tightly regulated by states and municipalities. And on the whole, these regulations are quite beneficial in that they guide the design and construction of systems that will serve their owners well while protecting the broader interests of the local community. In the past 3 lectures, we've seen raw water obtained from a distant reservoir, transported to our municipality, purified in a water treatment plant, transformed into greasy, contamination-laden sewage in your home, treated in a wastewater treatment facility or on-site septic system, and then returned safely to the hydrologic cycle. And we owe it all to water supply and wastewater infrastructure systems that are fundamental to our quality of life. Now let's turn our attention from water to another resource on which our modern lifestyle depends: electrical power. For most of the electricity we currently consume, the production of power begins with fossil fuel. In the next lecture, we'll dig into the subject of coal, oil, and natural gas. Fossil fuels, coal, oil, and natural gas, are the lifeblood of our industrial economy and are absolutely integral to everyday engineering. We see their influences throughout this course, from the use of vinyl siding and asphalt shingles in residential construction, to our upcoming lectures on electric power generation, home heating systems, the internal combustion engine, highways, railroads, and even landfills. To understand these systems, how they work and how they sometimes don't work, and how they contribute to our quality of life while also sometimes degrading our environment, we need to know something about the technologies used to extract fossil fuels from the Earth's crust. These extractive technologies are also fascinating engineered systems in their own right, and thus are well worth exploring. Let's begin with coal. Now, if I were teaching this course a century ago, coal would need no introduction. You'd probably use it to heat your home. It would power your principal means of long-distance transportation, trains and ships. The infrastructure of coal distribution, coal yards, coal wagons, coal bins, would be as ubiquitous as the infrastructure of electric power distribution is today. Well, today nearly all of the coal mined in the US is shipped directly to power plants and heavy industries like steel manufacturing. So we hardly ever see this stuff, even though we feel its influence every day. Coal is a black or brownish sedimentary rock composed primarily of carbon mixed with varying amounts of impurities, primarily hydrogen, sulfur, oxygen, and nitrogen. The coal deposits we mine today originated in the distant past, when layers of dead vegetation accumulated on swampy ground and then were covered with layers of soil and subjected to progressively greater pressure and heat. Over time, this compressed organic material was transformed into peat and then into lignite, a soft brown material generally classified as the lowest grade of coal, then subbituminous coal, then bituminous coal, and finally anthracite, the hardest coal with the highest carbon content. As a result of this formation process, coal is typically found in more or less horizontal strata called coal beds or seams, with the higher quality types typically found at greater depths. The principal deposits of coal in the US are shown here. Small amounts of anthracite in the east, bituminous in Appalachia and the central region, and subbituminous and lignite farther west. Coal is extracted from these deposits by two principal methods: underground mining and surface mining. Now, underground mining involves the excavation of tunnels and shafts to access coal beds deep underground. When I first mentioned the word coal, this was probably the first image that came to mind: grimy men toiling with hand tools in dimly lit shafts. This was the world's most common form of mining for millennia, until the availability of large-scale earth-moving equipment made surface mining more economical in most circumstances. Today, underground mining is used primarily for extracting coal that's too deep to be reached by other means. And the grimy men with shovels have mostly been replaced by high-tech machines. In the typical underground mine, a shaft is driven from the surface into the coal seam, where a maze of tunnels extends progressively farther outward as mining operations progress. Back in the day, these tunnels were excavated by individual miners who set off explosive charges at the head of each tunnel and then mucked out the resulting debris with shovels wheelbarrows, and carts. Today, both digging and debris removal are performed by this continuous mining machine, a low crawler-mounted vehicle that incorporates a fearsome-looking cutter head mounted on an articulating arm, and a scoop and conveyor system that gathers in the excavated coal and transports it away from the excavation. Until recently, most underground mines used the room and pillar method, in which regularly spaced pillars of solid coal are left intact to hold up the roof of the excavation. The obvious disadvantage of this system is that it leaves behind 40 to 50% of the coal in the seam. But since the mid-1990s, this limitation has been largely overcome by a new technology called longwall mining. Using this method, a track-mounted excavating machine moves along an exposed face of coal, often upwards of a mile long, shearing off and collecting up a substantial slice of coal as it moves, protected by these hydraulically operated overhead shields. After each pass, the machine and the shields are displaced inward toward the exposed face of coal, and the portion of the excavation that's no longer supported by the shields is allowed to collapse. Longwall mining is faster and safer than room and pillar mining, and it captures a significantly larger proportion of the coal contained within a seam. Regardless of the excavation method, the raw coal extracted from a mine requires considerable processing before it can be shipped to customers. This is accomplished at an on-site coal processing plant that washes the coal, crushes it into chunks of graded sizes, and separates the unwanted soil and rock. The greatest technological challenge in underground mining is ventilation, which is absolutely essential for evacuating coal dust and methane gas from the underground spaces. By law, these mines are ventilated by huge fans placed at the surface so they won't be damaged in the event of a cave-in or a methane explosion. Now, mine safety has improved considerably in recent years. Nonetheless, in 2010, 29 miners were killed in an underground methane explosion at the Upper Big Branch mine in West Virginia, apparently caused by a faulty ventilation system. New technologies notwithstanding, underground mining remains a very dangerous business. Now, safety is one reason why today most of America's coal comes from surface mining, primarily in a swath of western states from Wyoming and Montana all the way down to Arizona and New Mexico. These mines are particularly productive because coal beds in this region are significantly thicker and closer to the surface than the deposits back east. Western coal is mostly subbituminous and lignite with very low energy density, meaning that more of it is needed to produce a given quantity of energy. But it also has low sulfur content, which burns cleaner and thus reduces the costs associated with pollution controls. The principal method for extracting this coal is open cast mining. A term coined in the 1970s after its former name, strip mining, became virtually synonymous with environmental degradation. Here's how modern open cast mining works. On a strip of land, vegetation and topsoil are first removed and stockpiled. Next, the overburden, the soil lying on top of the coal bed, is removed, and the coal is dug out and processed for delivery to the customer. The sequence is then repeated for the adjacent strips of land, with the overburden from each new strip placed directly onto the worked out strip alongside. This fill is then regraded, covered with the topsoil that was stockpiled previously, and then fertilized and seeded with vegetation. In this way, land is continuously reclaimed even as the mining proceeds. Because of the flat terrain and predominantly horizontal orientation of the coal beds, these open cast mines are home to some of the largest machines on Earth, like this bucket wheel excavator, and the king of all mining machines, the dragline, which operates by sinking its 200 cubic yard bucket into the ground and then winching it inward like this. Amazingly, this machine is powered entirely by electricity, a vivid illustration of the interconnectedness of our civil infrastructure. This immense electric-powered machine is used to excavate the coal that's burned to generate the electrical power that runs the same machine. Along with coal's contributions to power generation, we must also recognize its serious environmental impacts. We'll consider the effects of burning coal in the next lecture, but for now, we'll just focus on the effects of coal mining itself, which can include destruction of wildlife habitats, altered landforms, dust pollution, increased erosion, decreased soil fertility, depleted groundwater, methane gas emissions, sinkholes, and underground fires. In the past few decades, federal and state laws have eliminated the worst abuses through stringent requirements for permitting, inspections, and reclamation of mined-out lands. Yet, the adverse impacts can't be entirely eliminated, and so they must be considered in our ongoing struggle to find the right balance between environmental protection and our ever-increasing appetite for energy. More on this subject at the end of this lecture. Next, oil. The world consumes over 90 million barrels of it every day. And even though oil fuels only about 1% of US electric power generation, it constitutes 40% of our total energy consumption. Petroleum products power our automobiles and aircraft. They heat our homes, cook our meals, and lubricate our machines. They serve as a base for countless industrial chemicals and plastics. Complain as we might about oil as a non-renewable resource, oil as a source of pollution and greenhouse gases, oil as a source of international conflict. We depend on this stuff for our standard of living and will continue to depend on it for some time to come. So let's learn about it. Petroleum is a naturally occurring stew of hydrocarbons, organic compounds consisting entirely of hydrogen and carbon atoms. A major component of the unrefined crude oil we pump from the ground is a family of hydrocarbon molecules called alkanes. An alkane is a chain of carbon atoms, each bonded to 2 hydrogen atoms, except at the ends of the chain, where each carbon is bonded to 3 hydrogens. As a result of this molecular structure, the general chemical formula for an alkane is CnH2n+2, where N is the number of carbon atoms. The simplest and lightest alkane is methane, C1H4, the principal component of natural gas, with 1 carbon and 4 hydrogen atoms. Now add more carbon atoms to the chain and you'll get ethane, C2H6, propane, C3H8, and butane, C4H10. These are all gases at room temperature, but each progressively heavier molecule has a higher boiling point and thus is easier to liquefy by pressurizing the gas. That's why we can buy liquid propane in metal bottles at the local hardware store, but we can't buy liquid natural gas. That's why butane, which is even easier to liquefy than propane, can be stored safely in a plastic pocket lighter. Pentane, C5H12, is the lightest alkane that's still liquid at room temperature. The molecules from pentane through octane are principal components of gasoline. Nonane through hexadecane are used for diesel fuel and kerosene. Heavier alkanes for home heating oil and the lubricating oil that's used in your car's engine. At C20H42 and heavier, the alkanes are actually solid at room temperature. We know this material as paraffin wax. All of these alkanes, along with other types of hydrocarbon molecules in varying quantities, constitute petroleum. This substance originated as marine microorganisms, primarily plankton and algae that accumulated on the bottom of the sea 10 to 600 million years ago. Over time, these organisms decomposed into compounds of carbon and hydrogen, which were embedded within sedimentary layers that eventually hardened to fine-grained shale called source rock. As the source rock experienced progressively greater heat and pressure, the organic material was distilled into petroleum and natural gas, which eventually accumulated in more porous strata of limestone and sandstone, called reservoir rock. Here it was retained, as geological movements of the Earth's crust sandwiched the reservoir rock between layers of impermeable cap rock, like granite and marble. Armed with a deep understanding of this formation process, geologists use a variety of technologies to identify possible deposits of oil and natural gas deep underground. These include satellite imagery to identify geologic conditions favorable for oil deposits, seismology, which involves directing shock waves downward into the Earth's crust and measuring their reflections to identify differences in the density of underground strata, gravity meters, which detect minute variations in the Earth's gravitational field, magnetometers, which detect variations in the Earth's magnetic field, and electronic sniffers, which can detect minute traces of hydrocarbons emanating from the Earth. Once a deposit of oil has been identified, the process of extracting it begins with this iconic apparatus, the drilling rig. At its heart is the drill string, a series of hollow pipes, each about 30 feet long, connected together with threaded couplers. At the bottom of the string is the bit, which excavates the borehole as it rotates. Immediately above the bit are several heavy sections of pipe called drill collars, which fit over the drill string and provide the weight needed to drive the bit downward through solid rock. The drill string is suspended from this steel tower, the derrick, with a huge block and tackle and a rotating fitting called the swivel. The derrick is tall enough to allow new pipe segments to be added to the drill string as the borehole goes deeper. At the base of the derrick is a rotating turntable, which is set into the deck of the drilling rig and powered by an electric motor. A 4- or 6-sided pipe called the Kelly grips the top of the drill string and is inserted into a similarly shaped hole in the center of the turntable. Through this mechanism, the turntable rotates the drill string while allowing it to slide vertically downward as the bit advances. After the drill string has advanced about 30 feet, a process called drilling down the Kelly, a new segment of pipe must be spliced into the string. It's not unusual for a drill string to eventually reach 3 miles in length. Thus, this splicing operation must be repeated many hundreds of times during a drilling operation. When we think of drilling, we tend to imagine a device like this one, which is operated by pushing downward and then, therefore, placing the bit in compression as we drill. But a drill string can't possibly operate that way. If we try to push this mile-long shaft down into the ground, well, it would simply buckle like that. The drill string hangs from the derrick, and so it must necessarily be in tension. And we rely on the weight of the drill collars and the drill bit itself to provide the downward force necessary to drive the bit downward into solid rock, like this. The drilling process relies on a specialized lubricant called drilling mud, a mixture of water, bentonite clay, and a few other ingredients. During drilling, this substance is pumped downward through the hollow drill string. At the bottom of the borehole, the mud lubricates the bit, picks up the rock cuttings, and carries them back up to the surface on the outside of the drill string, with the high viscosity of the drilling mud ensuring that the cuttings don't settle back to the bottom of the borehole. At the surface, the cuttings are separated from the mud, which is then recirculated back into the drill string. Drilling continues until the bit reaches a depth just above the expected location of the oil deposit. Then the drill string is withdrawn, and a steel pipe called the well casing is inserted into the borehole to keep it from collapsing inward. Once in place, the casing is supported and sealed by pumping cement slurry or mortar down through the casing, followed by a plug, followed by drilling mud. The high-pressure mud forces the slurry down to the bottom of the borehole and then back up to fill the open space between the casing and the walls of the hole. Once the slurry has cured, the casing is literally locked in concrete. After some additional drilling to reach the oil deposit, the well is then prepared for operation. Explosive charges are lowered down into the bottom of the borehole and detonated to create perforations in the bottom of the casing. A small diameter pipe is then lowered into the casing and sealed into position. This pipe creates a conduit through which the oil can flow upward, and together with the casing constitutes a double-walled barrier against leakage. Now, underground oil actually resides within tiny pores and fissures in a stratum of limestone, sandstone, or shale. To get this oil flowing into the well, additional measures usually must be taken. If the stratum is limestone, acid is used to dissolve fissures into the limestone, providing channels through which the oil can flow. If the stratum is sandstone, water mixed with a proppant, typically sand, walnut shells, or aluminum pellets, is pumped into the well at very high pressure. The high pressure fluid fractures the rock, and the proppant particles hold these cracks open so the oil can flow through them. This process, called hydraulic fracturing or fracking, is also used in the extraction of natural gas, as we'll see shortly. Even after these measures are taken, the area from which a well extracts oil is often surprisingly small, typically extending only a few hundred feet outward from the bottom of the borehole. The gushers you've seen in Hollywood movies do happen occasionally, but normally the flow of oil from a well is also quite small. The U.S. national average for in-production wells is only 11 barrels per day. Given the multi-million-dollar cost of drilling a well and the inherent uncertainty in finding oil deposits, it's clear that this process entails some significant economic risk. Now, at this point, drilling is complete. The drilling rig is disassembled and hauled away, and production equipment is installed to extract oil from the well. If the underground pressure is adequate to push oil to the surface without help, the free-flowing well is simply capped off with this multi-valve apparatus called a Christmas tree, which includes a connection to the pipeline that carries the oil to its destination. If the well isn't free-flowing, a machine like this one, the colorfully named sucker rod pump, is used to draw out all of the oil. Most free-flowing wells eventually stop flowing freely, at which time pumps like this one must also be installed to maintain production. Much of our petroleum originates with offshore drilling, a fascinating technology that, unfortunately, we won't have time to cover in this course. Suffice it to say that the offshore drilling process is fundamentally the same as for land-based drilling, except its execution is far more complex and much riskier because of the need to keep the offshore drilling rig stationary over the wellhead while perched atop several hundred feet of turbulent water. Of course, the stuff that flows from any wellhead, offshore or on, isn't quite ready for your car's gas tank yet. This unrefined crude is a mixture of oil, natural gas, water, and various impurities. Immediately after extraction, these components undergo preliminary separation at a processing facility, typically located right there in the oil field. Only after this processing does the stuff actually qualify as crude oil. Bulk crude is then transported to a refinery, over water by tanker ships, and over land by pipeline. Pipeline systems have a tree-like topology with many small branches feeding into fewer larger ones, which feed into a single trunk carrying a large flow to the refinery. Because of its high viscosity, crude oil must be pumped through pipelines. It won't flow on its own. A typical pipeline has a pumping station every 60 to 100 miles along its entire length. And at its terminus, a tank farm is used for temporary storage of oil. The oil refinery's principal function is to separate crude oil into its constituent alkane hydrocarbons through a continuous process called fractionating, which takes advantage of differences in the boiling points of these substances. In this process, the oil is heated to 700 degrees Fahrenheit and then fed into the bottom of a tower called a fractionating column. As a result of the molecular sorting process that occurs within the tower, the lightest hydrocarbons, methane, ethane, propane, and butane, are drawn off at the top. At the next lower level is gasoline. Farther down below are naphtha and kerosene. And at the very bottom is a heavy residual oil. With further processing, lubricating oil is extracted from this residual, and some of what's left can be used for asphalt and as fuel for oil-fired power plants. The remainder is sent to a facility called a coking plant, which cooks the sludge until there's nothing left but carbon. The typical refinery incorporates many other processes, such as removing impurities, cracking heavy alkane molecules to produce more gasoline, and improving the gasoline's combustion properties. All these processes are the work of chemical engineers who design and implement the elaborate industrial system that transforms unrefined crude, a geological product of our Earth, into the highly refined fuels that keep our technology-intensive civilization in motion. The natural gas that we use for heating, cooking, and generating electricity is methane, the lightest of the alkane hydrocarbons. In the US, about 1/4 of natural gas production is associated gas, meaning that it's found within and extracted from petroleum deposits. In these deposits, methane is often dissolved in the oil and kept in solution by the very high pressure underground. But as soon as the mixture is brought to atmospheric pressure at the surface, the methane comes out of solution naturally. Before the development of gas pipelines in the 1950s, this associated methane was seen as an unwanted byproduct. It was actually burned off in the oil field. Today, it's usually captured and piped to a gas plant for processing and sale. The remainder of US natural gas production is non-associated gas. That is, it's found in gas fields and in coal beds separate from oil deposits, but extracted using essentially the same drilling process we saw earlier. As it comes from underground, natural gas is mostly methane. Nonetheless, it still requires refinement at a natural gas processing plant to remove water vapor and impurities and to separate and capture small amounts of other gaseous hydrocarbons, ethane, propane, butane, and pentane. The finished product is then transported to customers through another network of pipelines aided and controlled by compressors and gates. Since 2000, there has been a revolution in natural gas production, resulting from the large-scale exploitation of shale gas, particularly in the US and Canada. There are large reserves of shale gas around the world, but until recently, they couldn't be exploited economically because shale is too impermeable. The gas trapped within it couldn't be extracted. The recent boom has been enabled by two important technological developments, both of which actually predate the current natural gas revolution. The first is horizontal drilling, which is used to maximize the surface area of the borehole within a shale stratum. This process requires a remotely controlled downhole drilling motor to control the direction of the borehole deep underground. The second technology is hydraulic fracturing or fracking, the process of injecting a mixture of water and chemical additives at high pressure down into the borehole to create fractures through which the gas can flow. Like many other energy-related technologies we'll see in this course, the development of fracking was stimulated by federally funded research and federal tax credits, initiated after the oil crisis of the 1970s. It took a while, but this investment has now come to fruition. Today, fracking has completely changed the economics of energy in the countries where it's being used. Because fracking has increased our technically recoverable deposits by about 50%, natural gas is now the fastest growing contributor to the US energy supply. Prices have dropped significantly, as has our dependence on foreign sources of fossil fuel. Yet fracking is highly controversial, largely because of its adverse environmental impacts, the extent of which aren't yet fully understood. Although fracturing fluid is 99.5% water, hundreds of thousands of gallons of it are used on a typical site. More than half of this fluid is eventually recovered, but the rest remains underground. And thus, at a given site, thousands of gallons of those chemical additives, friction reducers, rust inhibitors, and such, are left below the surface, with the potential to contaminate aquifers. Indeed, some cases of fracking-related groundwater contamination have been documented. Methane emissions have also been documented at both active and abandoned wells, and there's even some evidence that fracking has caused small earthquakes because the high-pressure fluid lubricates fault lines and thus promotes slippage along tectonic plates. Like the environmental impacts of coal mining, These effects are potentially quite serious. In my view, it's our duty as citizens to make well-reasoned judgments about whether the degree of environmental degradation caused by fracking is justified by the very substantial benefits that we all reap from these technologies, and about the extent to which government regulation should be imposed on the associated industries to minimize adverse environmental impacts. But before we can make such judgments, we really must also understand the processes by which these fossil fuels are transformed into the energy we consume in such vast quantities every day. And to this subject, we shall turn in the lectures ahead.